Okay, so this is also a ripple and these are ripples. These are symmetric disturbances of the water molecules. Okay, so they are two-dimensional in this case, and generally they can be three-dimensional or spherical in shape. Now we come to the concept of reflection and refraction, and um, there are some laws which are being obeyed during this phenomenon of reflection and reflection. So we start from the law of reflection, and what is this? So we say when a ray of light is reflected at an interface dividing two optical media, then what happens? Okay, so this is now a fact based on observation. The incident ray, the reflected ray, and the normal drawn to the surface at the point of incidence, they all lie in the same plane. Okay, and secondly, this is from calculation that the angle of incidence equals the angle of reflection, which we write this way. So theta I stands for the angle of incidence and theta r stands for the angle of reflection. And from calculations we came across this result that these two angles are the same. So for example, suppose this block over here, which you see over here, this is the surface of a medium. So this means this is one medium over here. You can call this to be medium 1, having refractive index in 1, and then this is a second medium uh, having a different refractive index labeled as n2. And suppose light is coming in the first medium. So this is now a ray of light which is coming this way and hitting the second medium, the surface of the second medium at this point. So this point is called the point of incidence or the point of impact. Now in order to find the directions of the incident ray and the reflected ray, what we do, we draw a perpendicular which is called a normal at that point of incidence. Okay, so light is coming in this direction, it is hitting the second medium surface at this point, and it is making some angle over here with that perpendicular or normal. This angle is called the angle of incidence, represented by theta I. And now from the observation what happens. The light, some part of the light is being reflected in that medium, in the incident medium. This part of energy is called the reflected ray, because this is represented by an arrow or a ray, and the angle found by this reflected ray with the normal, this is called the angle of reflection, represented by theta r. Small r stands for reflection. Okay, so now the first part of this law of reflection tells us that if the light is coming, for example, vertically, it must be reflected vertically. Okay, so for example, if you consider an imaginary vertical plane over here, what you see over here, the incident ray lies in that plane, the normal also lies in that plane, and the reflected ray also lies. This will be always true. This is why it is called a law of them. And secondly, these two angles must match, these must have the same value. So for example, if light is being incident on this surface, for example, and it is making an angle of 30 degree with the normal, so the light must be reflected in such a way that the angle between this normal and the reflected ray gain will be 30 degrees. Okay, now we come to the law of refraction, not reflection. This is also called Snell's law, and whenever you listen this word refraction, so this means light is going to enter from one medium to another medium. So two media are again the propagation of light in two media will be discussed over here, and there are some relations now. So when a ray of light is refracted now at an interface dividing two transparent media, then the transmitted ray remains within the plane of incidence, and secondly, the ratio of the sine of the angle of incidence, which is now represented by theta 1, to the sine of the angle of refraction in the second medium, which is represented by theta 2, this must be a constant. Remember, this ratio of the sine of the two angles in the two media must always be a constant, and this must have a fixed values. So although the angle of incidence and the angle of refraction may change, but this ratio of the sine of those angles doesn't change, it is fixed. So for example, again look into this figure, light is coming in some medium, so this is again, you call this medium number 1, and suppose the refractive index of this medium is labeled as N1. So light is coming in the form of ray, it is hitting this point, this is the point of incidence. Again you draw a normal, some portion of this light is being reflected, but now and some portion of this light now goes into the second medium. Okay, this is called the transmitted ray. Now we are not interested no more in the reflecting part of this, we are interested in that part of the light which goes into the second medium. Okay, so the incident light is making, again you draw a normal at the point of incidence, so this incident ray is again making some angle, and that angle we now label as theta I or theta 1, and the light which goes into the second medium, which is called the transmitted ray, this also makes some angle over here different from the angle of incidence. This angle is called theta T, T for transmission, or this is also labeled as theta 2. From observation and some calculation, we come across this result that the ratio of, if you take the sine of this angle and take the sine of the angle of refraction in the second medium and take the ratio, this ratio is always constant. So for example, if you now shine light at another angle, so for example this is another angle of incidence theta 1 different from the first one, what will happen? The refracted ray will also go into the second medium by a different amount, so theta 2 will be different. Okay, so this means the angle of refraction depends on the angle of incidence, but this ratio is constant, and this constant purely depends on the two media being involved in this process. So for example, what is the first medium over here in which light is coming initially, and what is the second medium over here in which light is going into. Okay, so this ratio purely depends on the two media, and that is why we write this constant value in terms of two numbers. One number is assigned to the first medium and the second number is assigned to the second medium. These numbers are called the refractive indices of the two media. So N1 stands for the refractive index of the first medium. For example, if this is air, and you know for air refractive index is 1, and N2, this stands for the refractive index or index of refraction of the second medium. So this can be water or this can be glass, and you know for water the refractive index is 1.33, and for glass, okay, so depending on the type of glass, it will have a refractive index ranging from 1.50 to 1.58 or things like that. And what is refractive index? This is the light for the, you can say, the wave bending ability. This is called the bendability of an optical medium. Okay, next is Huygens Principle, and this was presented in the year 1678. Okay, so Huygens presented his own theory of light about the propagation of light, and this is very much simple. And what are the main points of this theory? In this theory, which is called Huygens Principle, light is treated like a wave or a series of pulses which are emanated at the source of light and spreading or propagating in all directions. But this theory is unable to explain the nature of light. That means whether if light is a wave, so whether these are longitudinal waves or these are transverse waves. Okay, so Huygens principle or Huygens theory of light is unable to tell us about the nature, the longitudinal or the transverse nature of light. Secondly, it doesn't tell us about the wavelength of light. What is the wavelength of light? And it has no information about the speed of light. Okay, so all these informations are missing. Remember, these are the basic things associated with any kind of wave. Okay, so we don't see anything, we don't get it, any information of this kind from the Huygens theory. And this theory is based on a geometrical construction. Okay, so this means you have to draw some figures over here, and you treat the propagation of light in this theory in the concept of wavefronts, and then you say something. But the beauty of this simple theory is it allows to locate a wavefront if you know a wavefront at some time. Okay, so this theory allows us to locate or find the position of a wavefront at some later time with respect to the present location. Okay, so come to the statement of this principle, and according to this principle or theory of Huygens, all points on a wavefront can be considered as point sources for the production of spherical secondary waves, which are called wavelets then. Okay, so this principle has two parts. In the first part, light is considered as a wavefront. Secondly, the points on that wavefront are considered to be sources of new waves, which are called secondary waves or wavelets. And now the second portion, this now tells us the location after some time. After a time t, the new position or location of a wavefront is the surface tangent to these secondary wavelets. Okay, so let us come to the sketch of this. Suppose this is some wavefront, and remember this is now a planar wavefront. So this means some source of light is over here on the left hand side, and light is coming in the form of planes. Remember, this is the lateral view or the side view of those planes. Okay, so instead of planes we see lines over here. And remember one thing I forgot previously, that a wavefront and a ray of light are always perpendicular to one another. So for example, if you consider the light coming from this source in this direction, okay, so we draw an arrow over here, and this arrow is the ray of light. But if you consider that light to be coming in the form of waves, for example, I am just drawing that portion of the waves which is going this way. Okay, so these are called the wavefronts then, and you can see at each and every point these wavefronts, which are planar in this case now, okay, these are perpendicular to the ray. Okay, so they always form an angle of 90 degrees with one another. Okay, so this line, this vertical line now stands for a planar wavefront, and we name this, we label this is a wavefront AB. Okay, so this is a wavefront at the present time, which we call wavefront at time t is equal to 0. And now, according to Huygens principle, all the points on this wavefront are acting like sources of a new wavefront. Okay, so for example, if you label some points over here, suppose I am considering this point 1, 2, 3 and 4. You can take many points. So we are just considering a few points over here, and now according to Huygens, if I consider a point over here, so this point is now behaving, it can produce its own spherical waves or circular waves. Likewise, this point over here, it is acting like a source of new waves. So this means you can consider this to be a source, and you can then draw wavefronts, circular wavefronts around this in the forward direction, remember, not in the backward direction. Okay, this is not allowed, and this is because light is moving just in one direction, in this direction. Okay, so the energy left behind is minimum or almost 0. Okay, so we just draw half of the circles over here are the wavefronts in the forward direction. Okay, so this is acting like a source of new wavefronts. This point is acting like a source of new wavefront, which is drawn over here, and like this one, and this one. And now according to Huygens, if you draw an imaginary line over here, or an imaginary surface I should say, such that that surface is perpendicular to all these new waves, secondary waves or wavelets. Okay, so this will be the location of the new wavefront. Okay, so your wavefront AB is over here. What at time t is equal to 0, what will be its location after some time t, at a later time t? So this is now the geometrical construction according to Huygens theory, that you consider points over here and the wavefront has sources of secondary waves. You just draw the wavefronts are the sections of the waves in the forward direction or the propagation direction, and then you draw a tangent, a surface or a line which is tangent to all of these secondary waves, and that surface, if I label this is A prime B prime, different from AB, so we say this is that wavefront, this is the new wavefront, or the position or location of the new wavefront. इसका मतलब ये कि ये जो वेवफ्रंट आपको नज़र आ रहा है जिसका हमने नाम रखा है ए बी, तो कुछ टाइम टी के बाद ये यहाँ पर होगा, जाहिर बात है। तो इसको आप कहेंगे कि जैसे ये कोई नया वेवफ्रंट है, और इसको आप इस तरीके से हाइगन्स के थ्योरी के मुताबिक यह है कि कंस्ट्रक्ट करते हैं। ओके, दिस मीन्स दिस वेवफ्रंट हैज़ मूव्ड in a time t. This wavefront has moved how much distance in going from this old location to this new location? Okay, it depends on the velocity of the wavefront. Okay, and the distance between this old location and this final location, this distance will be just v times t, you know this. But remember, this distance is actually the radius of the secondary wavelets. So you can write this, you may see this in books written this way: the radius of the secondary wavelets over here, this will be v times t. And if this is light which is moving in vacuum or free space, then this will be c times t, where c stands for the speed of light in free space. Likewise, in the case of a spherical or circular wavefront, so suppose this is some circular or spherical wavefront labeled as AB. Again, according to Huygens, points, and this can be considered as sources of waves. So we just consider a few points over here. So for example, if I am talking about this point, so it can generate waves of its own. So for example, one of the wavefronts is shown over here, which is being generated by this point. Likewise, this point can generate a wavefront, new wavefront according to Huygens of its own, and likewise all the points can produce secondary waves or secondary wavelets. And what we do then, we draw an imaginary surface or an imaginary line which is touching all these secondary waves at just one point, which in mathematics we say this is tangent to all of those. This is called an envelope as well in mathematics. Okay, so this imaginary surface, this is the location of that wavefront after some time t, and we name this as a prime, b prime. It travels from this point, this location to this location in time t, and how much distance it travels as it moves from the old location to the new. Again, this will be just s is equal to v times t, or s is equal to the radius of these secondary wavelets. So this will be r equals, and if this is again light in free space, so this will be c times t then.